Hello everyone. We have already learned how electromagnetic waves behaves in free space. Behaves means using Maxwell's equation we have seen that how one can derive a plane wave solution which can propagate freely in free space, and homogeneous dielectric medium where sigma we consider 0, epsilon we consider epsilon 0 epsilon r, and mu we consider mu 0 mu r equal to mu 0 non-magnetic material where we consider mu r equal to 1 and epsilon r not equal to 1, mu r equal to 1 we consider. So, in that case we have got a solution like say electric field, say if it is propagating in a certain direction z t we can consider, then we can say that electric field can be propagating along x direction and it can have a constant amplitude, and you can think of monochromatic wave if it is positive direction propagating k z. Okay. And magnetic field we can represent as a y and is something like this e to the power j omega t minus k z. It is positive direction propagating minus k z, and if it is reverse direction minus z direction. So, this thing will be plus, minus will become plus. That is how we have solved, and we have shown that k will be basically k is nothing but k vector we consider like that k z a z direction if it is orthogonal direction. And in this case if you just see that wave, if it is just you take z direction, wave is electric field, if you just consider this is your x direction, then x direction you can see that it can travel like this sinusoidally, because real part will be just cos omega t minus k z. So, if you just take at any instant of time t equal to 0, you can see electric field will be like this. This will be your electric field will be oscillating like this, and this will be oscillating like this. Okay. And if you see that magnetic field, if you are just considering, say let me consider the another color something like this, then this is your y direction magnetic field, then you can say that magnetic field will be oscillating something like this. Okay. This is in yz plane, magnetic field will be oscillating in yz plane. We are just showing in yz plane. Basically this is going along y direction, this is your magnetic field. Magnetic field oscillates like this. Okay. And that is, and you can say that this electric field in this particular case, electric field and magnetic field, it is in phase. When electric field is increasing, magnetic field is also increasing, and when magnetic field decreasing, electric field is also decreasing. And if you try to see this one, this peak to peak, that is actually it will be lambda naught if it is free space, and if it is medium, then lambda by n. That is what we have seen. The one important part is that the solution itself is showing sinusoidally, and each time this value is actually going maximum to E0. That is one instant. Next instant of time this will be moving, this phase will be moving in this direction with a velocity that is called phase velocity will be omega by k. Okay. Omega by k, k equal to, as you know that k we have defined earlier, k equal to 2 pi by lambda. If it is material medium, it will be 2 pi by lambda over n. So, the phase velocity we can consider omega by p, and that means this phase will be travelling with a velocity like this, okay, travelling wave. And interesting part is that the maxima as it travels, it does not change E naught, always it is coming back to E naught. and by plus minus E naught, it will vary from plus minus E naught. Magnetic field plus minus H naught. Obviously, E naught and H naught, they are also related by eta. That is what we have learnt in the previous lecture. So, that means if it is a homogeneous dielectric isotropic medium, isotropic means that material property does not depend on direction, and homogeneous means material property does not depend on space, position. So, homogeneous isotropic medium, we have seen that the magnetic field, electric field is propagating without any disturbance. It will always come back and forth, E naught plus E naught to minus E naught plus H naught to minus H naught. Obviously, you should keep in mind that E naught H naught always perpendicular orthogonal direction, and this wave can carry energy. That carrying energy, we have defined that P equal to half average. If you are just consider average, you just consider real part of E cross H star. So, that is your average energy will be flowing, and that average energy, if you see here, whatever average at this point, if you see whatever the average energy at a particular distance, if you see that average energy flow will be constant. So, that means in free space and homogeneous medium, according to the material property we have used here, the electromagnetic wave propagates without any attenuation, no loss. Source can be somewhere, and from the source electromagnetic wave is generating, and that electromagnetic wave is propagating in free space or homogeneous medium, the homogeneous dielectric medium without any loss. The energy can flow, and it can flow as long as you want, as you can desire, and as it can travel as a function of time, right. So, that is what the idea. Now, what we would like to discuss here now, practically we do not get such thing. Of course, free space is there, but you do not handle with free space, you do not use free space to design your device, right. Free space is free space, you have to design or fabricate, manufacture your device using some material, and that material, as I said, that those materials can be categorized in terms of whether they are metal, whether they are dielectric, completely dielectric, and then they can be semiconductor also, conductor, semiconductor, so on. So, these three materials medium is there. So, in these three material medium, you can actually define material properties, say epsilon, mu, sigma, by choosing different set of value, but or in other words, you can say that metal has a certain value, range of values for epsilon, mu and sigma. Dielectric will have, obviously dielectric as we consider ideal dielectric, sigma equal to 0, and semiconductor we will see sigma equal to 0 or not. So, so far we have treated that is considering sigma equal to 0 and considering mu equal to mu r equal to 1, mu 0 is there, epsilon 0 will be there, and epsilon r it can be 1 or anything. In that case, no loss is there, we have discussed. So, now we will just consider if wave is propagating in a lossy dielectric medium. Dielectric, where we have considered ideal dielectric, where sigma equal to 0. Now, we are considering it is not really ideal dielectric, but some sigma equal to there, not equal to 0 is there. In that case, this is not ideal dielectric. If presence of sigma can actually hamper the propagation of electromagnetic wave or not, that is what we would like to see. And we will show that since sigma not equal to 0, you will see that this electromagnetic wave will be attenuated. If sigma not equal to 0, it will be attenuated as it propagates. So, there will be some kind of losses will be there. So, that is why when I am just considering sigma not equal to 0 and all other parameter I am considering epsilon r, some value is there, mu or some values are there, they are actually dielectric we can consider somewhat non-ideal, that is lossy, which means I am just considering sigma not equal to 0. I just start with Maxwell's equation once again, whatever we discussed in the previous thing, I just repeated here in a material medium. This is the displacement current, conduction current, and this is the charge things are there, everything is there. Again we will be considering this thing, right. Sigma we are considering, I think we should say much lower than infinity sigma. Its ideal conductor, normally we can consider sigma tends to infinity, high conductivity. Otherwise, it is much less than that in practical material, never becomes infinity, but you can have sigma value close to 0 and sigma value close higher than much higher than 0. So, we are considering some value is there. Mu r again we are considering non-magnetic material, dielectric non-magnetic material, epsilon r has some value. And same way we can just consider the solutions are like that, x, y, z dependent, space dependent and time dependent variations. This type of solution we can find from the Maxwell's equation for dielectric loss medium. So, if I just use sigma not equal to 0, then I have to put here j is equal to sigma e, I have to insert here, j d I have to put here, then the Fourier domain or frequency domain Maxwell's equation can be written as like this, because del t we know that del t equal to j omega, right. J omega we are putting curl E s B s j omega mu, and then this one will be there, j omega can be written here. And from this one we can write sigma E s will be there also, and j omega epsilon E s will be there. So, this one del t again j omega epsilon s, and this one equal to, simply we are writing this thing, this value. And e to the power j omega t term you can write here e to the power j omega t, here also e to the power j omega t, they can cancel, here also e to the power j omega t, here also e to the power j omega t, here e to the power j omega t, they can cancel. So, I get only the frequency domain, time dependent part can be cancelled, only space dependent solution. Only thing is that sigma non-zero, it brings this parameter now, new parameter, new term we are getting there. Okay. So, I just repeated here how it looks like. This one, this equation, these two equation I can represent something like this. By using you take a curl both side and this one curl here both side, then you get wave equation like this. If you are taking curl this one, we can write something like that, curl of this one, we can say that this one minus grad square E s, and right hand side will be minus j omega mu curl of H s, that can be written as this one equal to obviously equal to 0, I am considering charge free. So, I am considering del square E s equal to minus j omega mu. So, I can say that can be del square E s equal to minus cancelled. So, I can say j omega mu sigma plus j omega epsilon E s, okay. That gives me del square E s minus j omega mu sigma plus j omega epsilon E s equal to 0. Vector sign you should not miss, okay. That is what I have written here, that is what it is written here. This is the equation we get here. So, similarly, we start from here, we get this equation. Now, you see, we are using in this term, this one I am using as gamma square, I am just representing that one. Then I can express the electromagnetic wave equation, this one like this, gamma square E s. Similarly, this one will be like this. Simply I am just representing this one as gamma square. Okay. Now, same way I can try to get a solution. So, if you just think in this particular case, I have just for simplification purpose, if I consider that the electric field only have x component, okay, z component of the electric field is 0, just without any loss of generality, you can consider that, okay, just for understanding purpose, we are just considering electric field component has only along x component, okay. And also we can consider that that's electric field, earlier we have seen that it can be considered that it is x y independent, it is only propagating along z direction, it can be varying, I would say varying only z direction, and x y direction it is remain unchanged, you can consider. So, if it is remained unchanged, I can say that only electric field is z dependent. So, these two assumptions we are considering to understanding for understanding purpose. So, if I just substitute this one here, then I know that if I just try to get del x Es double, because this del square is nothing but del dou x2 plus this one plus. So, since the field is x independent, y independent, so these two terms will go. So, we will end up with only z dependent terms, and in that case I am just not using the vector sign also, because both side vector sign which is x direction. So, it is reduced to a scalar equation basically. Okay. So, for this we can have a solution, very interesting solution like this, just plus minus gamma z. Okay. So, you get a solution. Ultimately x dependent I am not considering, y dependencies, just z dependent, and forcefully I consider that electric field is oscillating along x direction. So, if it is oscillating along x direction, I have two choices. It can propagate, the wave can propagate in z direction or y direction. Okay, we will see in this type of situation what happens. Since we see that something exponential term coming like z like this, then I can say that okay, this is just taken same thing whatever derived earlier, or up till here we just got this thing, right. So, we have this thing, and then time dependent part I just put j omega t. There also we have just written this thing, time dependent part, this one I removed. So, this is written, and now we will little bit move here. Gamma, I have seen that gamma square is equal to chosen like this. Gamma square is a complex, and gamma value square root you have to take. Since we have taken plus minus, I have not put here plus minus, this sign I have not put here, because already solution itself it is coming plus minus over gamma. So, here I am just putting gamma. Since it is a complex value here in terms of material property, remember that if you are putting sigma equal to 0, then you see sigma equal to 0, if you put gamma value will be equal to square root of omega square mu epsilon and minus root over minus 1 means you will be getting j. So, that means you get j equal to j omega times mu epsilon, and mu epsilon means j omega mu 0 epsilon 0 and epsilon r, and mu 0 epsilon 0 if you square root if you take, that is nothing but j by it is minus j omega by, not minus, j omega by c, and epsilon are equal to n. So, this is basically c by n. So, gamma is appearing like a k value. So, once you put sigma equal to 0, it is a k like a homogeneous medium and free space, similar type of solutions you will be getting. So, in this case sigma not equal to 0, that is why we have to deal with it. Since it is a complex, we are just considering okay, the solution, the square root if you take, it will have a real part, imaginary part. Alpha is the real part and beta is the imaginary part. And if you just do little bit of algebra here, you can try to find out alpha value. If you just make a square root here, just squaring both sides, and if you do some trick, you can find alpha value in this form, and beta value. You can try this thing few steps, I just omitted here, the straightforward. Any textbook in electromagnetics you can find that. Okay. So, that means I see that gamma is now is a complex value, and this gamma appears in your solution, and it has a real part, imaginary part like this. The field attenuates as it propagates. How is that? You see, now I have electric field, this one I am writing z dependent part, E naught, consider x direction, I am writing e to the power j omega t plus minus beta z minus plus alpha z. So, if I am just writing this one alpha plus j beta, I am just writing plus minus, you are writing e to the power plus minus alpha plus j beta into e to the power j omega t. So, you are writing e to the power j omega t, j beta you are writing, and alpha z part I am just putting outside, because this is just like a phase, e to the power j omega t plus minus beta z, and this part is somehow alpha is a real value, plus or minus. So, if you consider plus or minus, you can always consider, always you know that this phase part, if you are considering plus and minus you are considering, that means wave is propagating along forward direction, positive z direction, and negative it is like a wave propagating along. If you are considering negative, that means it is a negative forward direction, positive backward direction. So, here it is written something like that. Negative means positive direction and backward propagating in the minus z direction. And minus z, since minus z, I can use here alpha z, because z if it is minus, that will attenuates, and here I can write also z equal to positive direction, z positive, it will attenuates. It will be oscillating, but as it propagates it will be oscillating. This is the difference. So, if sigma not equal to 0, you see that you are still getting a plane wave solution. You can assume a plane wave solution, but it is attenuating in nature. As it propagates, alpha is the positive value, positive number that can be defined like this. Then you can get this one. But you check here, if alpha sigma equal to 0, if you put sigma equal to 0, if you put, this one will go. That means 1 minus 1 0, alpha will become 0. So, for sigma equal to 0, alpha will be equal to 0. Then in that case, this will miss. This will miss. So, it is a solution like plane wave things. So, once sigma is there, you can say that the wave starting from Maxwell's equation, I can say that the wave attenuates as it propagates. Okay. Now, so I have just written down forward direction, reverse direction. Okay. So, forward propagating wave here, reverse propagating wave here, and plus alpha, whatever this is, because negative direction, that is why it is a lossy thing. I write plus, should not be confused that it will be amplifying. Now, magnetic field can be directly solved from the Maxwell's curl equation. Once I get electric field, I can find magnetic field here. This is x direction. I can solve this one. For example, curl Es, if you just see, you can just something like that, Ax, Ay, Az, dou x, dou y, dou z, and then I have electric field, I have only x direction. I have E0 e to the power j omega t plus beta z e to the power not minus, I can write e to the power minus alpha z. This is the thing 0 0. So, this is the thing, and right hand side I can put minus j omega mu, and I can write hx, hsx, maybe you can consider hsy, hsz. This is the 3 components. So, if you solve that, I can find the magnetic field will have in the y direction. If electric field is in the x direction, magnetic field can be considered as a y direction. This is a negative direction, sorry, this is a positive z direction, and this is a negative z direction. Now, if you see from here, I have the from this equation also, if you solve, one more thing you will be getting similar to earlier E naught by H naught. When it is lossy medium, sigma equal to 0, that will be coming like this. You just solve this one, substitute here, after substituting this one here for example, then you get magnetic field solution. At the same time, if you just take a ratio, it will be E naught by H naught, and if you know that ratio, if you are taking, that is also since sigma not equal to 0, alpha will be there, and if you just put alpha plus j beta explanation, we know that alpha plus j beta is nothing but we have j omega mu sigma plus j omega epsilon. So, instead of that, if I just put this one, then ultimately you are getting these equations, and that is actually we say that E naught by H naught, that is a characteristics impedance, intrinsic impedance for the material medium. So, now it is sigma value is there, so eta is there. If I just put sigma equal to 0, then eta will be, you can consider j omega mu by j omega epsilon, j cancel, omega may cancel, that is actually mu by epsilon. That is simple. That means dielectric, lossless dielectric medium, sigma equal to 0. If it is a free space, then eta naught will be just simply mu naught by epsilon naught. Mu 0 is Henry per meter, 4 pi into 10 to the minus 7, then you get 377 or 76, something like that, 70. Okay. this is ohm. So, that is what we know. So, now we have electric field and we have magnetic field, forward propagating, reverse propagating. And one important thing you should be noticing that in the reverse direction, when you solve, whenever you are solving this thing, using this one, you are substituting this electric field here directly and solving, then your magnetic field will be, you are getting with a minus sign, and if you are solving this one here, you are getting magnetic field with a positive sign. That means, whenever you are getting electric field with a forward propagating wave, then your magnetic wave will be in phase together, electric field, and that is only positive x direction, and this also oscillating in the positive y direction. But whenever it is, you are considering reverse direction propagation, that means beta is considered, instead of beta minus beta you are considering, that is why plus beta z, then minus sign will be there. So, that thing you should be keeping in mind, okay? That is what I have just tried to say. So, that means, if your wave is propagating in this direction, then this is your positive x axis, that is electric, that is actually x axis. For example, if you are considering AE, this is E field, it's like this, and this is magnetic field in the positive y direction. This is actually x axis, this is y axis, this is z axis, for example. Along this one you have magnetic field. So, wave is propagating like this. So, magnetic field will be, electric field will be oscillating like this, and magnetic field will be oscillating like this, so on in the x direction. So, that is how it will be propagating. At any instant of time you can find out what is the, if electric field phase is known, you know what is the magnetic field, which position and what is the value. But if it is reverse direction propagating in this direction, you see electric field you can consider x direction, but magnetic field you are showing like this, it is reverse at an instant of time. Same instant, if you are showing that if electric field is propagating in negative direction, magnetic field direction has to be changed. So, this is very important. Sometimes you know how it is defined. For example, you right hand rule you can consider, if this is a electric field, all the fingers, 4 fingers I am showing, that is the electric field, and magnetic field is x direction, magnetic field is in this direction, then it is propagating in this direction. If this is electric field, this is electric field, and magnetic field this direction downward, then it will be propagating in this direction. So, that is how it is, I have tried to represent here. Okay. And again, if you just try to find out energy flow, same way P average equal to E cross Z, because it is Z direction propagation, I am just written Z, then you find interesting formula like this, E cross H, because in E also you have minus alpha Z, H also you have minus alpha Z, if you multiply, then you are getting minus 2 alpha Z, and you know that E naught by H naught equal to eta, right. So, H naught I can represent with H naught, I can represent like H naught equal to E naught by eta, okay, E naught by eta, okay. So, this is actually mistake, I would suggest that this should not be there. So, it will be E naught by eta, E naught by eta, half E naught square by eta e to the power minus 2 alpha Z, okay. So, this is a typo error, I am sorry for that. All right. So, this means that energy as it propagates, it sees some kind of attenuation. Electric field and magnetic field also attenuates with alpha J value because of this sigma. So, energy also you will be seeing that as it propagates, energy will be dropping, okay. So, then this thing normally we can represent like this, half, this is again it should be eta, right, E naught, that is fine, and then this one can be represented as I z I naught e to the power minus alpha naught z. So, that means it is intensity. So, this can be written as amplitude square is basically power flow per unit time per unit area, and if it is per unit time, sometimes it is power flow per unit, energy flow per unit area, it is sometimes called as a intensity. So, I write I z equal to I naught e to the power alpha naught, where alpha naught equal to 2 alpha basically. That means, this alpha is the amplitude attenuation and alpha naught is the intensity attenuation, and we can represent like this, and this is basically known as Beer's law. Beer's law, Beer he derived first much before the Maxwell's equations. So, by experimental observations, that if it is lossy medium, the intensity how it is dropping, it is following exponential law, that is known as Beer's law, and this is now we can show that from the Maxwell's equation you can see that. But one important part you should be keeping in mind that this alpha naught sometimes it is attenuating lossy medium, but you can have a gain medium also. So, the light signal, electromagnetic wave, as it propagates, it can amplify. So, that amplification also can be represented by Beer's law. Instead of alpha naught, you can put a G jet, where G is the gain coefficient. So, that means this alpha we have represented in terms of, if you see previously alpha expression, sigma, this is alpha expression, right? This is your alpha, sigma, epsilon, mu, everything is there, that is alpha. That is why you are getting a negative alpha, as it propagates it attenuates. But if you have a gain medium, so how to represent gain medium and treat the Maxwell's equations? Then you have to modify this epsilon, mu, sigma such that it will be giving some gain. That means gain medium mathematically you can represent again in terms of omega mu epsilon by suitable change in dielectric constant, suitable change in conductivity, suitable change in magnetic, all these things can be done also. So, that means again I am emphasizing that Maxwell's equations is macroscopic Maxwell's equation, whatever we have discussed, that can be useful very easily for any structures, any material medium, and you can have lossy medium, you can have a lossless medium, you can have a gain medium, still you can actually utilize whatever the solutions we are getting from here. Now, we will see that since sigma non-zero we have explained, now we will be trying to understand that just not lossy medium, if it is just a metal, practical metal we are using, just dielectric with some loss medium is not sufficient, towards ideal metal, ideal conductor, ideal semiconductor, then what would happen? Okay? Because these things, as I mentioned earlier again and again, that any photonic integrated circuits, all this material is very important to realize different type of devices. So, electromagnetic wave, light wave, how it interacts with those material medium, you need to know.